You can think of DDPG as just, as I mentioned earlier, you can think of DDPG as a generalization of DQN to continuous action spaces. Okay. So, what was our DQN algorithm? Do you remember? Like, what was the main objective we had? We wanted to have some estimate of, we wanted to find Q star, right? If you know Q star, we know optimal policy, right? If I give you Q star, what is an optimal policy? If I give you Q star, what is pi star? You just take R maths over A, you get your pi star, right? So we wanted to estimate what is Q star. For that, what did we do? We wanted to find an estimate of what Q star is, right? So we denoted something called Q hat of STAT, which is parameterized by some weights W. Let's say we want this function to approximate our Q star, right? In the DQN, that's what we did, right? Like, I'm just trying to briefly recap what is DQN. So in the DQN, what was our loss function? We want this to closely resemble what? We want to find a neural network which will take the state action pair and gives us what? Q star, right? So we wanted it to closely resemble Q star of STAT. So we were minimizing the mean square error, right? This is what we wanted to minimize in the DQN, right? Minimize over all W. Then if you solve this problem, then you will get a neural network with weights W, which will take any state action pair as input and gives you an estimate of what is Q star. So for implementing this, what did we do? Like, we don't know the actual Q stars, right? So what did we do at the Q star position? What did we substitute here? It will be RT plus 1 plus gamma times Q hat of maths over A, Q hat of ST plus 1 comma A, right? This is what we did, right? If we don't know what is Q star, so we just substituted this value instead of Q star. Now, so how did we, like, how do we compute this yellow term, like the bottom one? How do we compute this? RT plus 1 we'll see, like we'll take an action AT, RT plus 1, the environment will give us RT plus 1. And then how do we get the remaining term? So we have looked at two ways of doing this, right? One way is you take your neural network, you input your state features to the neural network. There is some neural network which will take your state features. Let's say there are two actions, only two actions possible. Then what could be done? Like, you will get Q of S comma A1 here, you will get Q of S comma A2 here. Like, this is one architecture we discussed, right? You just input the state features to the neural network. The neural network will output you the Q value for every possible action. If there are two actions, then the DQN neural network will give you two outputs, which correspond to the Q value for the left. Let's say you're looking at the cart pole, which has only two actions, right? The left and the right. So you just input the cart pole vector state feature, which is a feature vector of length 4. Then you'll get two outputs. One output corresponds to the left Q value, one output corresponds to the right Q value. This is one way. So assume, let's say now you have a continuous state space of actions. Your actions are from a continuous set. Do you think you can do this? Here we had two actions, so we kept two outputs for the neural network, which correspond to the Q value of each action in that state. So let's say my action is a real number, right? So then will this architecture work? No, right? Because how many outputs we should have? If A is a real number, we should have infinite outputs, right? Because for every action, we want to know what is Q. Based on that, we are computing what is the maths over A, right? Because if you want to compute this maths over A, you need to know what is a Q value for every A. So if you had a finite number of actions, you could have done this. But now you have infinite number of actions. So how do we deal with this is what the DDPG tells us. Okay. So this is one architecture. What was the other architecture we discussed for the Q learning? So instead of this, we could have also done this. Like let's say these are the state features, like state features, and you also input, let's say, action. Like let's say action is a binary vector, like in the cardboard, it's a binary vector, binary number, right? One may be right and zero may be left. You input that also here, then maybe you'll get one value which is q of s comma a. So once you will input a equal to 1, then you will get the action value for the left action. Then you again do one more forward pass. You again input a equal to 0. Then you will get q of s comma 0. Then you do, if there are two actions, you have to do two forward passes. Then you will get both the q values. And then you take the maths over them. This was one action. Even this won't work for us, right? This is even more, right? Because there are a lot of actions for us. We cannot do forward pass for every action that is possible because we have an infinite number of actions, right? So these two architectures won't work. So instead of that, what DDPG tells to do is, like this is all DQN. So you understood the problem, right? Because if you try to do DQN with continuous set of actions, it's not straightforward because we can't compute this maths. So what we do in DDPG is we want to learn a mapping from state to action. This is like learning a policy itself, which is roughly equal to, let's say you have let's say there is some current Q function. You have some Q function and you want to find this thing. This is our main problem, right? So let's say someone gives you a Q function. We want to find what is the maximum argument according to that. So what we'll do is we'll find, if I call this as a star of s, I'm trying to find a function which is equal to a star of s. I'm trying to find a function which will directly give me a star of s. Okay. So that is like my Q of, so I want a mu which will satisfy this property. The maximum Q value, this is what I have to substitute in my update rule, right? Here I have to substitute this value. So I'm trying to find a mu which will give me this, or which will roughly be equal to this. Okay. Mu theta is a deterministic mapping from mu theta is a function from state space to action space. Is this goal clear? Huh? Because we are doing some neural network approximation. You cannot. Yeah, it takes in S and gives you an A, which is directly this argmax over A. So this is like a learning a deterministic policy. If you can find given a Q, given a Q, we are trying to find a mu, which is a policy, which will satisfy this thing. Like we want it to be equal to, if we can't find it exactly, we'll approximate it. That's all. Okay. Because this is the problem we had, right? We are not able to compute Q value separately for each action and then take the maths over A. So we wanted to find a mapping which directly maps your state to an action and whose Q value is the best Q value possible. So we'll discuss that. Like this is the idea. Like it's like learning a deterministic policy. Okay. Huh? For the current Q, this will give you. We don't know whether Q is equal to Q star. If Q also, if your Q converges to Q star, your mu will converge to mu pi star. Huh? Mu is a function which takes a state and gives you action. It is parameterized by a theta vector. It is like a parameters of a theta policy or something. How are we? No, here also this is like you can think of mu as a neural network which will take S, and let's say your action is a real number. It will just give one real number as output. So let's say your A is a real number between minus infinity to plus infinity. It's like a regression, right? You take in some state features, you give you one real number as output, where A is the A, which is the argmax over Q of S comma I. Is this problem setup clear? Because it was tough to find maths over A, we are directly trying to learn mapping from the S to the best action according to our current Q. Okay, let's say we start with some arbitrary value, like we start with some arbitrary parameters theta. Okay, let's assume we have this mu theta with us. Then, then what will, then how can we update our Q based on that? Because all that we were stuck is with this maths over A, right? Now, if I give you a mu, can I do this Q learning? Because here, what can I substitute instead of this RT plus 1 plus gamma times maths over A? This term is there, right? So let's say, like I had this term. What is the problem with this term for me right now? I don't know how to compute this maths over A Q of S T comma A. Let's say someone gives us this news. Let's say you have some current estimate of your news. Then what can I write this as? RT plus 1 plus gamma times Q hat of ST plus 1 comma mu theta of ST or ST plus 1. What? No, this was the action taken in, okay, ST plus 1. Which is weighted by some parameters W. Like Q had this weights W, U has the weights theta. Okay. So now I know how to compute my this term. Then I can do the semi-gradient updates, right? What will be my updates? It will be the difference between this term versus my this thing. Okay. Is this clear? Because that's the only hurdle we had. Rest of the thing will be the same. We'll have a target queue network, we'll have a replay buffer. You can do all those things. Whatever we learned in the queue learning, we had some target queue network and we were updating, we are computing the targets based on that. And once in a while, we are updating our targets. And we had a memory replay buffer to make sure that the subsequent states are not correlated. We randomly take one S comma A from that and then do the updates. Everything else will remain the same, except this, instead of this max over A, Q of A, we'll just do this one. Okay. Huh? What was W? W are the weights of the Q hat. That's what we started with, right? So we have two neural network. One neural network is Q function, which is which has the weight W. And we introduce one more neural network for the mu, which is like a policy, right? Is this clear? Now the question is, how do we suppose we start with some mu, then we know how to do the Q learning updates. Now our mu also is, we have to learn the mu also, right? So this is the Q learning side we understood. Now we have to understand what happens, how do we train the theta parameters. Okay. So how do we train the theta parameters? So let's say someone gives you the Q function. Like what was mu theta for us? For a given Q, it should give you the best action in best mapping from state to action, right? So let's say there is a Q function which is given to you. Like that is your current estimate of your neural network. W's, you have that Q function. Then what is that we want the mu to satisfy? Uh, this we want some theta which will maximize this. Let's say for a particular status, we want to find what is the best action, right? So for every set of theta parameters, you'll get some Q value. You want to find the theta which will maximize this, right? This is for a given status, but we want for all the states, right? Because for a given status, if you just maximize only for that particular state, will maximize. But as we have been doing in the policy gradient methods, also we are defining our objective as uh, like expected V pi of S, where S is coming according to some distribution, right? So similar to that, we are writing like this, where S is sampled according to some distribution. So we want to find a theta which will maximize the Q value. Okay. So we can do gradient descent for this kind of a stochastic gradient descent for this kind of a problem. Okay. So this is how we learn. Okay. So you alternatively keep doing this. You start with some arbitrary mu. You start with some arbitrary theta parameters. Based on that, you update your Q weights. You start with some arbitrary theta parameters, and based on that, you update your Q weights by minimizing this loss function. Okay. Then we'll get some new Q values, like new weights for the Q function. Then using the new weights for the Q function, you again update your theta parameters using this loss function. So you keep doing this iteratively. You improve your theta vector once, then you improve your W vector once. You keep alternating between these two steps. Based on your current mu, you will improve your W's, and based on the W's, you fit a new parameters for the theta. Okay. So this is also, as I said, this will be very similar to the Q-learning, AQN, except for this change. So here we are having, this is also an offline method. You can have memory replay buffer. You can have target queue network. All those things you can implement here also. So if you want a good material to read about this is the OpenAI blog. There is a blog on OpenAI website which has DDPG and DD3. Both these things are described in detail. So you can look at the OpenAI blog. So this is a reference. So this is about DDPG. Maybe so. Although there might be some missing parts, but at a high level, do you understand what is DDPG? So as I said, the Q function will be something. The Q function will take like this. Like you have some features for the states. You have some features for the action. Like features, the action itself is a feature, right? Like say action is a number between minus infinity to plus infinity. That can be your feature for the action. Or if you have a 2D action, let's say, then you'll have two features for your action. A like X component of the action, Y component of the action. You'll have two action features, right? So this kind of architecture is not possible here. The first type of architecture is not possible, but the second type of architecture is possible. You input your S and your action state and action features, and then you'll get your output. So any doubts in this part? So and one thing to note is this DDPG is useful only for continuous action spaces. It's not useful for discrete action spaces.